Okay. So now, so what we did last class, basically, last class is to estimate the value, right? Estimation of a value or whatever the causal parameter, right? This is one of the causal parameter, right? So remember two type of parameters, right? One is the model parameter. So model parameter is whatever the model that we use, either outcome model or propensity model, right? Whatever the model we want to identify, right? The model is used to identify the potential outcome from the data, right? So last, as we discussed the last, causal inferences, working group, the identification is key. So once you identify, if you have the identification formula, then that means you can make a model for that identification, right? So then because of the identification, we can estimate the parameters in the model. So that is the one part. But our real ultimate goal is a causal parameter, right? Causal parameter. So what are the causal parameters we learned so far? One, chapter 2 is this, right? Potential outcome. Not potential outcome. The average iterative ATE. So there is one particular causal parameter. But another causal parameter is actually this guy, right? Potential expected value of the potential outcome under a given particular D, right? So that is another important causal parameter. So this is very general because this one actually includes this, right? Because you choose whatever option, then you basically estimate. So basically, this is the whole problem, main problem. Okay, although there may be another one like a conditional average tree. So that's another story. But even the marginal, we have two different causal parameters. So what we studied last class was basically using the outcome model approach, right? So remember, we always have an outcome model approach and then propensity score, right? Propensity score model approach, and then combined, right? Augmented propensity. So that's kind of a typical thing. So we are going to do the same here, okay? So now let's try to remember what we did for k equal 1. So that's actually the topic of the chapter 3 already, right? So I just copy and paste the same lecture note for the chapter 3 part. So that's basically k equal to 1. So just x and y, right? And y is single x, and y is just the potential outcome, right? And then in order to do this IPW estimation, we defined this concept, delta. So that is we call it regime consistency indicator, right? Where the observed, so given D, right? Given the decision rule, we can use X, right, to obtain the outcome, right, under this regime, and then check whether the regime the option using X is consistent with what we observed here in the data. So data is basically an indicator 0 or 1, and then we use that, and then all you have to do is compute the conditional expectation of this guy, which is this guy, right? So conditional expectation of delta. So basically, this is property of delta equal 1 given x. But this delta equal given this guy is actually the property of A equal dx given x, right? So you can actually use so all you have to do is, if you have pi a x as a property, a equal to small a given x. If you know this, right? If you know this, all you have to do is to replace a small a by dx, right? Because this is a conditional expectation of the random variable a given x. So property, so the randomness is about the capital A, right? And this is just a constant, either 0 or 1, right? So this one, basically, but we already know, we already have the form as this one. Okay. So for this one, all we have to do is replace A by dx, which is this one, right? So that which is basically we only have to dx x. Okay. So that is basically this guy. So that is for k equal to 1. Now, what about the k equal greater than 1? Well, we'll generalize this concept. So basically we have multiple options, multiple times. So for each time, we can actually construct the indicator. Okay. So A1 is equal to D1, A2 is equal to D2. But D2 is actually uses the history. So then we can decompose it as something like multiple product of the k indicator functions, right? And then so then we can conceptually create the same idea. So basically we have a numerator delta, which is a product of the k, right, indicators, and denominator is the same thing, but now you have this product of the conditional where this pi d, so subscript. So notice that this is a kind of, as I said, derived, right? Derived from propensity, original propensity AX. So that's for single, but for case, we have a K, basically. So all you have to do is what kind of option, right? What kind of option it takes and use it. So that is basically the idea.
Go ahead.
So in that design, so if any of this decision A is not equal to 0, 1, so it will basically become to 0 because of this contribution, right?
So
if any of
this 0, then 0, right? So so you can see that if K is really large, then we may end up having no, right? It's possible, right? But for now, but that violates the positivity assumption anyway. So in concept, as long as the positivity assumption holds, then if sample size is large, then we should have this proportion exist.
So for the last equation,
Okay.
the bottom of the slide, so we're summing over A to K, so that's just the decision at that little K.
K, right?
So it's just a 0 or 1.
Yeah, right.
And so it's
That's
not
right.
like, it's not, for example, going like saying a 1 at step 1, a 0 at step 2, and then a 1 at step 3 or something like K.
No, so this is for each K, right? So okay. So the causal parameter of interest, which is value, is a function of the potential outcomes. But the data is based on the observed realization of the potential outcomes, right? So that means we need to identify. So we need different identification rule, right? So we already have an identification rule here, but this one does not treat A as a random variable, right? It's a given, so A is a separate. This is we treat Y as a random variable, and this is the identification formula for the outcome model approach. But now here we are talking about the propensity score model approach. So that means we are using a model for A, right, to identify. And here's the main result. So basically why this is identification, because this one is a potential outcome. The right side is a potential outcome, while the left side is a observed data, right? So as long as you establish equality and you can estimate one side from the data, then you are in a position to, you can say that the model is identified, right? I mean, it's not really model is identified, whether it's in the context of the potential outcome framework, the potential outcome parameters are estimable from the data, as long as your model for this one, whatever, is correctly specified. Okay. So point is, making a model for the right side one directly is difficult, because you don't observe this one, right? You don't observe x star y star directly, but the left side is you observe this. You can observe this. So the idea is, let's try to make a model. Try to build a model for this random event which is observable, so that you can do something. You can estimate it from the data. So as we did in the last class, I'm going to use only k equal 2 to demonstrate the idea without losing the any fundamental principle. So k equal 2 should be enough to give you what's going on behind all this. So basically, if k equal 2, then this guy denominator is just 2, product of 2, and this one is delta 1. Delta is only product of the 2, delta 1, delta 2, and then g is any function. Okay, any function, and x bar is x1 and x2, right? So this one is actually 3 random variables, g, x1, x2, and y. So that means it is g over x1, x2 potential outcome, xy potential outcome for given b, right? Given for the rule for any regime, we can basically so this is the ultimate goal. This is what we really want. Okay. So let's try to, yes, it's a little bit confusing, but hopefully it makes sense.
So in this sense, can you go back to the previous?
Sure.
Z can be any
Huh?
Z can be any function.
G is any function. So for example, G can be Y. Okay, so that will basically compute the value. Okay, so but we actually, the result is actually can be any parameter. Okay, so first of all, let's write. So pi d1, what is this? We don't know this randomness, right? But we do know this. So A1. So we treat it as A1 and A2, capital A1, A2 random variable. So these are basically the propensity score function. So pi d1 is this one. So which is the A1 equal to the property of A1 equal to Gx1, T1 x1. This guy is at the second, right? Second at the decision k equal 2. So the decision k equal 2, we use the x1, x2. And then basically this is the probability given x1, x2, and a1. Okay. So first of all, on the SRA, right? So this is a potential outcome. So potential outcome, condition A is conditionally independent of the condition potential outcome given the history. So the first line should be true. And then this guy. So this is the for, basically this is for k equal 1. This is for k equal 2. So for k equal 2, so this probability. So I think we want to simplify. So this guy is this one, right? And this guy is this one. So we want to so the first probability best we can write this way. Second one, we eventually want to write it as a function of given potential outcome. Okay. So how we can get this one? Where maybe so we use sequential ignorability carefully. So basically A2, right? Given A2, so given the history, right? So given the history for A2, the history is x1, x2a, right? Given the history, A2 is independent of y star. So that's the first equality. And then second equality is that the conditional on x2 is equivalent to this. Okay. So you can this one you write it in terms of the observed one, but it's actually same as this one. So condition on this one. So then basically that means what? That means your event, random event probability can be written as something else.
So actually,
Yes.
I understand that x2, a1, but how you draw for a1?
Okay. I think that's actually same as the same proof. There's actually I think this is same as this one in some sense, because if you look at so
Right, but
here.
That one, the one you're dealing with is A2 data, right? So here is we have like the potential outcomes data.
Same.
You
So
use
you can use that's a very good point. Actually, so remember I kind of last class I tried to just say that, but then there's some confusion, right? And I sit down in my office and work out details, and then eventually see intuitively, right? I mean, intuitively see this one. So x1, x2. So forget about whatever it is. Let's just focus on what is conditional on. Conditional on, you have x1, x2, and a1. But at end of the day, you get what? x1 and x2 star for a1, right? So conditionally, it's the same, right? So that's actually takes a few line, two more line to establish that. So I think you can actually do the same thing here, but I haven't worked out. So but intuitively, right? If you just start from here to here, intuitively, well, is this really true, right? You might ask whether this is really true. But the answer is actually yes, right? Because of these steps. So because of these steps, we use under the sequential ignorability, conditioning on this one is exactly equal to conditioning on this one for y star. But for A, it's the same. So, I think. So anyway, so that's true. So there's actually some, maybe there's some step, two line steps, not really, I haven't worked out, but should be correct. So maybe you can check. Okay. So then now, what is interesting is that, so by Sutba, in the summation, right? In this here, we only care about the event, the case where delta equal to 1. So what do you mean by delta is all equal to 1? So delta 1 equal to 1 means what? Means my observed x2 is equal to the potential x2 on the D1, right? Same way, what do you mean by D1 and D2 equal to 1? That means my potential outcome for so my observed x2 is equal to this one. And also my observed y is equal to the potential outcome of y on the D1 and D2. So that means, so this implies this equivalent. So what's the difference? The left side is written in terms of the observed data, while the right side is written in terms of the potential outcome. Okay, but they are equal because if they are unequal, it's 0. So the equality holds as 0 equal to 0, right? If delta equal to 1, then we know that x2 is equal to x2 star d, and y is equal to y star d1 and d2. So they are equal. For delta equal to 1, they are equal. For delta equal to 0, they are not equal, but that doesn't matter, right? So something like that. So that actually gives you a very good property. So now you want to take the conditional expectation of this guy, given potential outcomes. Okay. So given the potential outcomes, all you have to do is everything is fixed. The only thing is random is delta. So that means your expectation is about the delta, which is your expectation is about A. So which gives you this pi d, because we already approved this one. So we have now cancellation. So in order to get this cancellation, we need to have a positivity, right? Assumption. Okay. So we use the positivity here, sutuba here, and the SRA in the very beginning. So we use 3 conditions to identify the model, the parameter. Okay.
One.
Sure.
In page 6,
Page 6. Okay.
in the second line.
You mean here?
Yeah, right. Why is
It's a semi-prime.
depend on A1 equal to D1 x1? Is that the definition of ID2?
So
You need to define that somewhere.
pi d, okay, pi d2. So this is the definition, right? So pi d2 means that d indicator d2 is equal to a2, and so we just use the, okay. So that this one is what? Property of AK, which is, so I see where you confusion. I mean, where you why you're asking. So A1. So because
Now, we do not have a A1 in in the argument, okay.
Well, actually, so that's good question. I guess. So, okay, let me. So A, K, we have two ways. One is AK is a X bar. Okay, let's use as K plus 1. Then X bar K. So two ways. One is this. The other one is in terms of potential outcome. X1 and oops, sorry. Yeah, that I see a point. X2 star. So because A1, we are actually using that. So this one, right? For example, okay, this one is not down. This one. So we have actually two equivalent expressions. One is the so we A2 is random, and then what is what we are conditioning on? So originally you could one way is using the potential outcome. So given the potential outcome, you can define A. Okay, that's one way. Another way is given the history, observe the history, you define the way. So this is actually the same. So that means when you write this way, you are actually, if you this expression itself means this is actually property of X A2 is D2, right? Given X1 and X2 star D1. This guy is equal to A2 equal to D2 given X1 and X2, observed X2, and then A1 equal to D1. I should. Let me. Okay. So let me just write, because what is your question is what is T2? So this one doesn't depend on A2 because it is actually right. A equal to actually T2. The A2 is what? A2 is sequentially X1, right? No, A2 is actually, sorry, A2 is, yeah, D2, X1, and X2 star D1. Okay, so that's one way. Another way is using the okay. Yes.
So when you write something like X2 star or the parentheses D1, is that saying that for a decision that we know or like it's not like a random decision or something that's unknown?
So it's a fixed function of the X1, X2.
Yeah, so is X2 star D1, is that saying like the potential outcome of X given a decision D1 that I already know that I'm taking? Or is it under any decision made at D1?
So given D1.
Yeah, even, so the point is that within the decision.
I should write it D1.
So it's for a specific.
If this is decision have time.
Yeah.
But it's not saying for any decision that is made at
Time.
step one.
I think,
So two. It's like in the. It's very similar to G formula actually. So remember in the G formula what we did. So it's spoken about. I mean, so here is you can think it as a y. Okay, if you treat y, use y. Okay, your x1 is actually. So I hope that this is A1, A2. A1, A2, given x1, x2 star A1, right? So this is the density, conditional density in terms of the observed data. While this is the conditional density in terms of the potential outcome, right? They are equal. That is the G formula, right? Same thing here, right? So basically this guy is written in terms of potential outcome, while this one is expressed in terms of the observation, but they are equal. So this is the outcome model version of the G formula, and while this one is the propensity score model version of the G formula. So remember, and then maybe this one is so another same thing. You can write it as a1 equal to t1 x1, a2 e2 e2 is what, x1 and x2, right? So if you write this way, this is purely a function of the observed data. While you can write is y star given put as a potential outcome, you can write it as x1 x2 star t1 given x1 x2 star t1. So these two is equal. That is the basically the G formula. So this G formula is with respect about the outcome model, while this G formula is about the potential outcome. Yes.
Basically, what we're saying when we use these different notations is basically, so looking at like x2 is we know the potential outcome of x2 for a specific decision rule at P1, because essentially there's the exact same information there as just observing x2 and knowing how we got there,
But
as long as those decisions are the same.
so T1 is a function of x1, but Tx2 star has a stochastic nature,
Yeah, it's great.
right? It's random, right? But T1 x1 is not random. It is as a function of x, is a deterministic function of x1.
This is a decision that we made in the, like, in the previous time, right? With the deterministic function, because we made the decision.
Like T is a rule that I already have, right?
Yeah,
So given the rule, I input the x, then I know which A will be chosen. Question? All right. Okay. Okay. So I hope it makes sense to you. So now what is the, well, IPW is, I personally don't like IPW because it's high variance, right? Usually it has a high variance. I mean, as a, it's kind of Horvitz-Thompson estimator, right? So we are using the, basically kind of, suppose I know this probability, I can conceptually the design-based, design unbiased estimator. So as a concept, right? I mean, it's very nice and maybe easy to compute, but it's statistically it's not really. I mean, practically it's not really good. But it may be a good as a building block to start as a start. So so denominator term in the Horvitz-Thompson can be interpreted as the propensity score for receiving the treatment constant with the regime D through all K decisions given the observed history, right? So it depends on the propensities of the treatment option given the observed history. So see, this is, so this is the, A is just data, right? H and A is just the data you have. And D is what you want to consider, right? You have a, you want to consider several different rules and then basically use that to compute this weight essentially. And now in order to learn this propensity score function estimated, then we need a model. So that means we may need this kind of models, but so how to do that? Well, we basically use data, right? So this is the data I have. So we use this data to construct the multinomial type distribution, right? I mean, so by, if A is all binary, A1 is binary, A2 is binary, it's just a logistic, I mean, paranoid type distribution. So conceptually, you should be able to estimate the parameter from the maximum likelihood. So this is basically likelihood function, right? Of your observed data from the parametric model. So then you can do, okay. So the bottom line is that it's based on the assumption that propensity score models are correctly specified. In some sequential randomized design, the model is known, some experiment, so then it should be relatively easy. But in the pure observational study, this is a very strong condition, actually. Except for estimation propensities, these estimators use data only from subject with. So remember, end of the day, right? Our estimator is this one. So the Y that we use is actually only for the case with the delta equal to 1. So this delta can be most of them will be 0, right? So even though this one is design unbiased, so this is very few of them will be 0. I'm sorry, very few of them will be 1, and everything else will be 0. But then the probability denominator will be very small, right? So then overall it cancel out, but maybe high variance, right? So that is the one of the disadvantage. So for large, especially K for large than very few such a subject, so can be unstable. because of the large variance. Denominator is small. And even if some cases you can experiment, for example, you know the propensity, but turns out that it's better to estimate it even though you know the truth. So that's similar to what we studied in the missing data class. Okay, so that's the IPW estimator. But now we're gonna improve, right? So we want to improve the IPW estimator using the projection and augmentation, right? So, so that that's exactly similar to what we did for k equal to 1. So we are doing the same thing. So here's the observation. So suppose you k equal 10, right? But so k equal 10, and you have a 10 visit. It turns out that first 8 are all consistent, but the last 2 are inconsistent, for example. So that's kind of a end of the day, it will be 0, right? Delta will be 0. But suppose k were 8, that's good, right? If the suppose the decision was stopped at 8, then it was valid, right? Observation you would use. So then you can actually sequentially think. So then maybe you can sequentially check, right? Until it broke down, right? The consensus broke down. So that means at least up to this point, I have information. Which information is the information I have this one. So basically what I observed is consistent with the current decision rule of the potential outcome of the current decision rule, right? So that is a partial information I have. So that means your observed one for this part is you can actually, so because potential outcomes are conceptually unobservable, right? But as long as it's consistent, right? Consistency holds, then we can use the observed data and make sure that they are matches. So that means we can actually treat this one as observed data, observed part of the data, and treat the others as a missing data. So that means in terms of the receiving trip options consistent with D, the individual has dropped out at this okay. Okay. So that is that basically brings the framework of the monotone missing data problem. So I'm going to use this toy example. Okay. So here's a very simple but helpful, supposed to be helpful for example that you can think of. So k equal 2. So k equal 2, that means you have a delta is delta 1, delta 2, right? So that means what? That means, so what is delta equal to 1? So delta 1 means what? Delta 1. Okay. So this is a given. So the important thing is D is given, right? So this is basically, you can say dx is d1 x1, d2 x1 x2. But I observe A, so I don't observe. So I observe. So okay. I use my X. I use the observed X and apply to this function D and see whether this dx is consistent with my observed A1 and A2. right? So the consistency holds. That means this under the rule that I have, this one is the same as my observed A1. My D2 will be same as my observed A2, right? That will be the case where delta 1 equal to 1 and delta 2 equal to 1, right? So in that case, I observed all potential outcome for that case, because I know that this basically means my observed y is the same as the potential outcome of y for that choice, right? So this is basically the argument here, right? And then what about delta 1 equal to 1 and delta 2 equal to 0? So this is interesting. So delta 1 equal to 1 and delta 2 equal to 0 means that my observed A1 is equal to my observed D1 X1. But my observed A2 is different from D2 X1, right? So that means what? That means so my potential outcome T1, usually usually this one I don't observe, I don't know, but because I know that this one, so X2 is what? X2 is X2 star 1 I 1 equal to 1. Okay, so so I know that my X2 is either X2 star 1 or X2 star 0, right? I know this my X2 is one of the two. But if delta equal to 1, delta 1 equal to 1, that means my observed A actually matches with my observed A1 is matches with the D1 X1. So that means my observed X2 star D1 is equal to 2, right? So this one implies this.
So as long as we can observe D1, then we can get the potential outcome expressed, right?
Observe the D1?
D1, yeah. As long as we can.
D1 and then use observe and then we compare with my observed A and then determine whether it is consistent or not. So if
we can get the expressed.
so if it's consistent, then we can accept it as an observed data, right? So my observed data, I always observe this one, but the problem is that I'm not sure whether this one is this one or this one, right? So basically it says that I can say that X2 is actually observed data. So this X2 is observed data, but because delta 2 equal to 0, that means for Y is not consistent. So my observation is not consistent with my potential outcome on the D. So then we can treat Y star as a missing data. So that it becomes a monotone missing problem. Okay. So that means because of the monotone, right? So here 0, 0 means what? Delta 1 equals 0, delta 2 0 means that I don't observe any potential outcome because my observed X2 or my observed Y are not consistent with the potential outcome under the D, right? So that means these are missing data. So that means we can actually use this monotone missing data structure to apply the theory of the monotone missing data propensity estimation. So augmented IPW estimator. Basically, this is the IPW. First of all, IPW, and then this one and this one basically has a partial use partial information. So because X1 is, if everything is missing, right? Even everything is missing, I still observe baseline. So at least this function is all available to me, right? So that's why we have a summation over I equal to 1. So this is any function. And then the last term is equal to 1 when delta 1 equal to 1. So when delta 1 equal to 1, we observe, so two cases, we observe X1 and X2 star. So I know that my X1 and X2 star, so my observed X1 and X2 are actually valid ones. So that means I can use, okay? So that means I can, any function of, so this is unbiased for any function over L1 and L2, because the expectation of this guy is cancels equal to 1, so cancels. So it's 0 expectation. This one is also 0 expectation. So these two elements are actually what? Belong to augmentation space, right? So that is the what we studied, augmentation space. But and then for k equal 2, in general, we can write this way. So if we just don't ignore anything, right? If we ignore this one, then it's just the IPW estimator. But we should use it, right? So we should use it. And then nice thing about monotone missing data is that the best choice is already known by theory of the Robbins. He proved this, right? So you can just use it. So basically, this is the what? This is the Q function. I mean, conditional expectation of the potential outcome. And this one is actually, you can use the G formula to estimate beta, and then plug in to here to obtain the efficient. So then the efficient AIPW estimator can be written as this way. And then actually, I also covered this similar thing in my NRI class meeting. And so basically, you have you use the best information. So basically, if these two are observed, then you can actually compute the residual using X1 and X2. If for this one, you actually have two different models. One is the model using the X1, X2, while this one is the model using X1 only. So you can kind of improve the. So if you take the expectation, this one cancels, so they are unbiased. But this is the kind of a best, most efficient, efficient one. Okay. So this is doubly robust, right? Doubly robust and locally efficient. And this is,
Okay.
yeah.
Yeah, so we just mentioned that if we go to the next slide. The next one.
Okay.
So can be implemented using calibration weighting
Yeah.
for the potential.
Yeah. So that is, so I'm going to explain this concept. So I originally I just say that, but I'm kind enough to make a few more slides to explain the concept. So in homework 4, so that's why I so emphasize that you should do homework, right? So if you do the homework, you know that this is the important condition, right? So this is what covariant balancing property. Covariant balancing is really important, right? in survey sample is calibration. But basically, as long as you make the weight to satisfy this, you don't have to worry about anything, right? And so on the, I mean, this is, if you, the implicit model behind it is a linear. So, but it can be, if you have a nonlinear, and if you can somehow create a basis function, then you can basically use the basis functions to the calibration to get the covariant balancing. Then basically all you have to do is to use this final rate, satisfying the covariant balancing as the estimator for ATE estimation. So this is for AT estimation. And then furthermore, so there's actually many ways of satisfying this. One particular way is you use this one as an objective function to optimize, then actually it will create the doubly robust estimator, right? So that is the homework problem. So actually I already also made the solution. So if you are not really sure about the answer, you can check. Now, here's the key idea. Now this is for ATE. Okay, then next question is, what would be the calibration equation or covariant balancing equation for estimating the value for this one? Okay.
Could you ask a quick question?
Yeah.
So in page 18, so this is a particular objective function, right?
Right.
So basically, there's a whole group of objective functions that can satisfy
Right.
the efficiency of a double basket.
Right.
But this one is probably the most simple one.
Yeah, so this is something that as a homework problem. Other things you need to, it's not really close form, but this one particular is good because you can actually work out as a homework problem. Now, here's the kind of my idea. So basically, this is a missing data indicator. Apply, obtain calibration. Then it will create a value, estimate of the value using the observed data. That's it for K equal 1. And then you can actually, so this is actually pure learning, right? Because we are using so this is actually the outcome model. I mean, why we consider this one? Because it's the outcome model says that it's a linear. So same thing here. So this is a Q learning essentially, Q learning estimator. And if you want to make it doubly robust, then you should use this kind of right? So that will take care of the value estimation using the propensity calibration weighting for K equal 1. What about K equal 2, 3? It's possible, but I'm not going to tell you because I need to write a paper. So I will make it, but you guys can think about that and I'll be happy to discuss with you. I don't know whether somebody already wrote a paper on this idea. I don't know, but I think at least should be potentially, oh, sorry. Not even meeting. I think